How does using a graph of observed data from a blackbody radiator versus a theoretical prediction of the data help illuminate problems with the theory? One of the nice things about graphs is that they show you a lot of information in a very easy to read format. So let's assume that the experiment or observation was properly done. Then whatever theory you have must absolutely match the data. If not, you need to modify the theory or possibly create a new one. The case of the intensity versus wavelength for blackbody radiators clearly showed a discrepancy, a major one, between the blackbody's observed and its theoretically predicted behavior at 5,000 K. The theoretical graph showed that the intensity would go to infinity. In reality, that's not what happened, so therefore the graph helped us see that. However, can you see a really big problem with the classical theory prediction? Again, that's over here, this curve at 5,000 K, and here's the measured data at 5,000 K. So, and of course, green and red were also measured. This is 3,000 K, this is 4,000 K, but this is the one that would correspond here. So I think I've already given the hint. What's wrong with the theory? The classical theory shows that the intensity of the emitted radiation, that's this curve here, you can see that it's coming off the chart here, and you can imagine it just keeps on going, and you don't have to imagine, that's actually what the theory says. So it's approaching infinity as the wavelength gets shorter, which is not at all what happens. You can see that the intensity of the higher frequency, the lower wavelength light, it does increase, and you can see it moving to the left, but it gets to a peak, and then instead of continuing on to infinity, it comes down. Okay, so shorter wavelengths means the light is moving into the ultraviolet end of the spectrum. Hence, a quite dramatic name was put on this. It was called the ultraviolet catastrophe.